Well, hi there. Now that we discussed Fourier transform concept and equations, let's solve some examples. A quick reminder, if you want to find the Fourier transform of x of t, which is called x of omega, you need to calculate the integral from minus infinity to infinity of x of t e to minus j omega t dt. Notice the integral is with respect to time t, so you're left with omega, you get a function of omega. On the other hand, if you are given x of omega and you want to go back to x of t, evaluate the Fourier inverse of x of omega, which is 1 over 2 pi integral minus infinity to infinity x of omega e to j omega t d omega. Notice this time the integral is with respect to omega, which means omega disappears and you're left with time t for the signal x of t. For our first example, consider the signal x of t equal a rect t over tau. This is the all familiar rectangular pulse. It has amplitude a and the width of the pulse is tau. This is a periodic signal. It does not repeat itself. The question says calculate the Fourier transform of x of t, which is x of omega. And once you find x of omega, sketch its magnitude, called magnitude spectrum density, and sketch its phase, which is called phase spectrum density. This is a simple problem. All I have to do is use the Fourier transform integral, which is integral from minus infinity to infinity x of t e to minus j omega t dt. When you substitute x of t, which is the single rectangular pulse, you substitute 0 everywhere except from minus tau over 2 to tau over 2, where the function x of t is a constant a, and then multiply by e to minus j omega t dt. Take a outside. The integral of the exponential is exponential. Of course, remember to divide by the constant minus j omega. Then substitute the limits, minus tau over 2 to tau over 2. You're going to get e to minus j omega tau over 2, as you can see here, minus e to plus j omega tau over 2, because the minus here cancels out with the minus here. I took this constant outside. Now let's switch the order of the exponentials to get rid of the minus sign. You get e to j omega tau over 2 minus e to minus j omega tau over 2. I'm going to let the j inside, multiply by 2, divide by 2. This of course reminds you of sine. So I'm going to replace this term with sine omega tau over 2. Multiply by pi, divide by pi. Same thing here. Multiply by the value of pi, divide by pi. Multiply by tau and tau here as well. This is the definition of sinc, which is sinc omega tau over 2 pi. I'm left with the constant a tau at the outside. This is x of omega, or the Fourier transform of a single rectangular pulse. Please notice that the sinc is a real number that could be positive or negative, but it is a special case of a complex number. So you can calculate the magnitude of x of omega, which is the absolute value of a tau sinc omega tau over 2 pi, and the phase of x of omega, which is 0 degrees if the sinc is positive, or 180 degrees or pi if the sinc is negative. This is the right answer for the magnitude of this complex number and the phase of this complex number. If you sketch the magnitude of x of omega versus omega, you're going to get the magnitude spectrum density. And if you sketch the phase of x of omega versus omega, you're going to get the phase spectrum density. This is the magnitude spectrum density, absolute value of x of omega, which is the absolute value of sinc. Notice that the maximum value is a tau, because you have a tau sinc omega tau over 2 pi. And notice that the first null occurs at omega equal 2 pi over tau, because substituting 2 pi over tau for omega here gives you sinc 1, which is the first null of the sinc. For the phase spectrum density, the angle of x of omega, notice that when the sinc used to be negative, I have pi here for the phase, and when the sinc used to be positive, I got angle 0, and then pi, and then 0, and so on. I hope you notice that because the signal x of t is aperiodic in this example, what I got for the Fourier transform are smooth curves for the magnitude spectrum density and for the phase spectrum density, unlike what I get for periodic signals, which is a group of impulses. Also notice here that because my x of t, which is a rectangular shape, is real valued, what we got is even symmetry for the magnitude spectrum density and odd symmetry for the phase spectrum density. Because this magnitude spectrum density and this phase spectrum density are very simple answers, I can combine them into one diagram, which I call the amplitude spectrum density. Notice here I sketched the whole complex number x of omega, including sign. So the sync shows up when it's positive and when it's negative. And many times this is quite sufficient because all the information that I need is contained in one diagram rather than two. By the way, now you've seen magnitude spectrum density and amplitude spectrum density. If I ask you what is the bandwidth of x of t, the single rectangular shape, you want to say, I'm going to look at x of omega and see where are the significant components of the frequency domain and where are the insignificant components. For sync, usually we consider the first null, the point that separates significant stuff from insignificant or negligible stuff. I know it's an approximation, but it's a good approximation that many people use. So you can say the bandwidth of this signal is 2 pi over tau in radian per second, or 1 over tau if you want the answer in hertz. This rule of first null is similar to what we've done for a repeated direct signal. By the way, people use this rule of first null for sync shape, sync square, sync to the power 3, sync to the power 4, sync to the power n. For those shapes, first null is a good approximation of the bandwidth of the signal. Another observation to keep in mind, because it might help you if you want to memorize the answers for those basic functions, is that the answers we get for Fourier transform of aperiodic signals like x of t equal a rect t over tau have a lot of similarities with the Fourier series answers we get for the periodic versions of those functions. For example, repeat every t naught of our a rect t over tau. If you recall, we calculated the complex exponential Fourier series form for this repeated direct signal. Turns out the answer is alpha n a tau over t naught sync n omega naught tau over 2 pi. And this answer looks quite similar to the answer we got for a single rectangular pulse when we did the Fourier transform. We got a tau sync omega tau over 2 pi. You notice there are only two differences. Here we don't have t naught. Here we divide by t naught, which makes sense because t naught, the fundamental period, only exists in periodic signals. It does not exist in aperiodic signals. Another difference is that this omega here is a continuous variable, while omega here is n omega naught. It's a discrete variable that is multiple of the fundamental frequency. The observation here is that if you memorize one of those answers, say the Fourier transform of a single rectangular shape, you can easily memorize the Fourier series and hence the Fourier transform of repeated rectangular shape because the modifications are quite simple to do. This second example is a homework for you. This time consider the signal x of t a single triangular shape, a delta of t over tau, which has magnitude a and a pulse width of 2 tau. This signal does not repeat itself, it's aperiodic. Find the Fourier transform x of omega and draw the magnitude and phase spectrum densities. Here is the correct answer, a tau sync square omega tau over 2 pi. Obtaining the answer is not difficult, it's just time consuming, and it's quite similar to the calculations we've done in the case of Fourier series for repeated triangular shape. I want you to do the calculations yourself to find the correct answer, but because this example is a bit lengthy, let me give you some hints. Use the Fourier transform integral, substitute x of t, which is the equation for the triangular shape. Of course, you know that from minus tau to 0, the triangular shape is a linear line with positive slope, but from 0 to tau, it's a linear line with negative slope. And then split again the integral. One part here, a multiplied by the exponential. One part is a over tau t multiplied by the exponential. Split the integral here into 2 again. A multiplied by the exponential minus a over tau t multiplied by the exponential. The integral of the exponential functions is simple. It's just exponential, while the integral of t multiplied by exponential can be done by parts to get this answer here. Now substitute the limits minus tau to 0 here and here, 0 to tau in the other two terms. You're going to get this equation. Rearrange some terms. The 1 and minus 1 go here. The exponentials go there. This is a common factor which you can take outside. These cancel out. You can swap the order here and then multiply by j omega and divide by j omega here. And if you multiply by tau here and divide by tau, this term cancels out with this one. This term cancels out with this one. And then you can take this e to minus j omega tau as a common factor outside, which allows you to convert those four terms into a square using this formula. After that, take e to j omega tau over 2 as a common factor, which will cancel out with this term, but this here reminds you of sine, that is squared. Now rearrange a few terms, you're gonna get sinh square, which is the right answer. Please remember that sinh square is always positive, so the magnitude of x of omega is the absolute value of a tau sinh square omega tau over 2 pi, which is equal to a tau sinh square omega tau over 2 pi, and the phase of x of omega is always 0 because x of omega is always a positive real number. Here is what the magnitude spectrum density looks like. This is sinh square. And here is the phase spectrum density, which is 0 all the time. This is a very simple answer. I can combine both diagrams into the amplitude spectrum density, which is our frequency domain representation of a single triangular shape. This Fourier transform result shows that the components after 2 pi over tau are negligible and can be considered almost 0. So the bandwidth of this signal is 2 pi over tau in radian per second or 1 over tau in hertz. Please practice finding those answers on your own and then compare those answers to the ones I've shown here. It's also interesting here to notice that if you memorize the Fourier transform of the aperiodic x of t of a single triangular shape, which is a tau sinh square omega tau over 2 pi, you can easily remember the Fourier series of the periodic version of the signal, which is repeat every t naught a delta t over tau. Because the answer for this one, which we found earlier, turns out to be alpha n a tau over t naught sinh square and omega naught tau over 2 pi. Notice the similarity between this answer and this answer. The only two differences you'll find is that there is no t naught here, this is aperiodic, and you divide here by t naught because this is periodic, and instead of continuous omega, we've replaced it with discrete omega equal an omega naught. Those are the only two differences, and this makes memorizing the answer quite simple. Now let's move on to the third example. X of t equal a single impulse or Dirac delta signal, a delta of t. This impulse is located at time equal 0 seconds, and the area under the impulse is equal a. What is the Fourier transform of this single impulse? We'll use the Fourier transform integral. The integral from minus infinity to infinity, x of t e to minus j omega t dt, and substitute here a delta of t. We can take a, the constant, outside and then use the sampling property of the impulse, which says that the integral of an impulse multiplied by a function gives you the value of this function at the location of the impulse, which is t equals 0. So I'm going to get e to minus j omega t here, substitute 0, which is e to the power 0, that's 1, and the value is a. So we figured out that the Fourier transform of a single impulse located at time equal 0 seconds is actually equal constant in the frequency domain, which I show you here. The value of x of omega is equal a over all frequencies omega. It's a very interesting special case. Please memorize it because this result is quite useful. And also leads me to ask the other question. What if x of t is constant in time domain equal a? So x of t is equal a constant, which is, by the way, a DC value. So I want to find the Fourier transform of a DC value, or a DC shift, or a DC offset. What is the Fourier transform of this signal? Unfortunately, this is not as simple as the previous example, because we cannot just use the direct integration here, because x of t equal a is not absolutely integrable over the period minus infinity to infinity, meaning it does not satisfy this condition which says I need the integral minus infinity to infinity of absolute value of x of t dt to be smaller than infinity. Please substitute a here and verify that this integral gives you infinity, so the condition is not satisfied. This doesn't mean that there is no Fourier transform. It just means I cannot use the integral directly to find the Fourier transform. However, I'm going to use a simple trick here, because the answer turns out to be a very simple one. What I'm going to do is guess the answer and verify that it is the correct answer by performing an inverse Fourier transform. And if the inverse Fourier transform gives me the original signal A, then I found the answer correctly. So what should I guess for the answer? Remember from the third example that the Fourier transform of an impulse was constant. So let me just take a guess that x of omega is equal an impulse, and that impulse is located at 0 frequency. So my guess is x of omega equal 2 pi by the constant a delta of omega. Is that the Fourier transform of constant a? Let's verify it by calculating the Fourier inverse of x of omega. If my guess is correct, this Fourier inverse will give me x of t back. I hope you remember that Fourier inverse is 1 over 2 pi the integral minus infinity to infinity of the Fourier transform x of omega e to plus j omega t d omega. This is not dt, this is d omega. Now substitute my guess x of omega, which is 2 pi a delta of omega. Now let's use the sampling property of the impulse. Please remember that this delta of omega is located at omega equals 0. So the result of the integral is this function at the location of the impulse, which is omega equals 0. So substitute for omega 0, I'll get e to j 0 multiplied by t. Of course, I took the constant 2 by a outside. The 2 by cancels out. E to 0 gives you 1. You're left with a, that's your x of t, which is the x of t we started with. So we proved that the Fourier transform of a constant or a DC shift or a DC value or a DC offset, is actually an impulse, and that impulse is located at 0 frequency, so long as you remember to multiply by 2 pi. This is what the Fourier transform x of omega looks like. Please remember, it's the Fourier transform for a constant. So we've seen that an impulse in time domain has a Fourier transform of constant in frequency domain. On the other hand, a constant in time domain has a Fourier transform of an impulse in frequency domain. This is a property I hope to teach you later on called duality of Fourier transform. Another interesting thing to keep in mind is that x of t equal a is a DC value, which can be represented in Fourier series using alpha naught. And alpha naught, which is Fourier series, can be converted into Fourier transform by multiplying by 2 pi and converting it into an impulse. So this impulse is actually alpha naught, which is a, multiplied by 2 pi, and this value of a was converted into an impulse. So the answer makes sense, and that's how I easily guessed what the answer is going to be for this problem. Alright, question 5 is a homework for you. You are given the Fourier transform x of omega, which is an impulse, 2 pi a delta of omega minus omega naught. This is an impulse that is shifted in frequency, and the amount of shift is to the right by omega naught. So I say, find the inverse Fourier transform and tell me what is x of t going to be. Remember that when we had constant a in time domain, we got an impulse around 0 in frequency domain. I ask a question, what signal x of t in time domain gives you a shifted impulse in frequency domain? Please do the Fourier inverse and prove that x of t here is a constant a again, but this time multiplied by e to j omega naught t. This is actually an interesting result that you should memorize because it is considered a property of Fourier transform. The Fourier transform of a signal x of t constant multiplied by e to j omega naught t gives you 2 by a impulse because of the constant, but because of the e to j omega naught t, you get this shift of minus omega naught. By the way, if you're wondering what is the Fourier transform of a e to minus j omega naught t, then because of this constant you get 2 by a impulse, but because you have a minus here, you get a shift plus omega naught, which is shift left in frequency by an amount of omega naught. Another homework for you to practice, you have x of t exponential e to minus at u of t, which looks like this. Determine the Fourier transform x of omega and sketch the corresponding magnitude and phase spectrum densities. The correct answer is x of omega 1 over a plus j omega, for which you can calculate the magnitude and the phase and draw the magnitude spectrum density, absolute value of x of omega, which looks like this, and the phase spectrum density, angle of x of omega, which looks like this. Notice that the magnitude spectrum density has even symmetry, while the phase spectrum density has odd symmetry because x of t is a real valued signal. The seventh example is very important. You should memorize the answer because it shows up in a lot of situations. The question says, for the signal x of t equal a cosine omega naught t, which is a cosine of amplitude a and fundamental frequency omega naught, determine the Fourier transform x of omega and sketch the corresponding magnitude and phase spectrum densities. I'm going to solve this problem using two techniques. You'll see I'll get the same exact answer, which I hope you then memorize. In the first solution, I'm going to remind you that this signal is periodic. And because it's periodic, I can find Fourier series. And from Fourier series, I can convert that into Fourier transform. Not only that, but I'm going to find the complex exponential Fourier series simply by inspection. Because this signal x of t equal a cosine omega naught t can be written using Euler's identity as a e to j omega naught t plus e to minus j omega naught t over 2. So this cosine is simply two exponentials. And this exponential with the frequency omega naught has an amplitude a over 2. So alpha 1 is a over 2. This exponential with the frequency minus omega naught has amplitude a over 2. So alpha minus 1 is a over 2. All the other alphas, including alpha 0, alpha 2, alpha 3, alpha 4, alpha 5, alpha minus 10, alpha minus 20 are zeros. This is a very simple answer that you should know for a cosine. Now let's convert those alphas into Fourier transform. To do that, you multiply each alpha by a factor of 2 pi and convert the values of alpha n into impulses at their corresponding frequencies. What I'm gonna get is a over 2 multiplied by 2 pi and then multiplied by an impulse. Notice the impulse is located at omega naught, which is the frequency of this exponential. For alpha minus 1, I have a over 2 multiplied by 2 pi multiplied by an impulse. And this impulse is located at minus omega naught. This is shift left. So minus omega naught, which is the frequency of this exponential. What I'm getting here is two impulses of area by A by A. This impulse is shifted, so it's located at omega naught, and this impulse is shifted, located at minus omega naught. So the final answer, x of omega, is two impulses, one located at omega naught, area by A, another one located at minus omega naught, area by A. This is a very important answer. Please memorize it. But I can also obtain the same exact answer if I use the integral definition of Fourier transform, which says that the Fourier transform of x of t is the integral minus infinity to infinity x of t e to minus j omega t dt. I'll substitute for x of t a cosine omega naught t and then expand the cosine using Euler's identity. This exponential multiplied by this exponential can be integrated by itself, and this exponential multiplied by this exponential can be integrated by itself. I took the constants outside the integral. Now look at this integral. This should remind you of an integral of a signal multiplied by e2 minus j omega t dt. That's actually the definition of Fourier transform. But I'm doing Fourier transform for e to j omega naught t. Same thing here. This integral is the integral of a signal e2 minus j omega t dt. That's the Fourier transform of e2 minus j omega naught t. But there is no need to calculate this integral because I already gave you an earlier example where we said the Fourier transform of a constant, let's say 1, multiplied by e to j omega naught t is equal to 2 pi by the constant, say 1, delta of omega minus omega naught. This is the answer of the Fourier transform. The other Fourier transform that you need is constant e2 minus j omega naught t, and that gives you 2 pi by the constant delta of omega plus omega naught. So from those answers, we can substitute here 2 pi multiplied by 1, delta of omega minus omega naught, and we substitute here 2 pi multiplied by 1, delta of omega plus omega naught. The answer is exactly the same two impulses I got earlier. One shifted right and located at frequency omega naught, one shifted left located at minus omega naught. Both of them have an area of pi a and pi a. You should memorize this essential answer because cosine shows up in a lot of engineering systems. And now you know its Fourier transform, which is two impulses at frequency omega naught and minus omega naught. Remember that in Fourier series, two lines give you one harmonic cosine, and in Fourier transform, two impulses give you one harmonic, that's a cosine. Now your homework is to try this sign. What if x of t is a sine omega naught t? Determine the Fourier transform x of omega for that signal and sketch the corresponding magnitude and phase spectrum densities. What you will find out is that the answer is also two impulses, as you can see here, one located at omega naught, one at minus omega naught, but you have this extra minus j here and this extra j here. Try to find this answer using two techniques like I did. First, find Fourier series converted into Fourier transform, or use Euler's identity to find the Fourier transform. That's all for this video. I'll be happy to hear your comments and questions. This is Muhammad Hawa. Bye-bye.